Alright, so the next problem, I believe this is the last problem in this section, is 28. And for this, we're given the probability of having a boy is 0.51, and having, well, that naturally equates of probability of having a girl would be 0.49. So those two values are given, and we want to find within a family of 5 children, what is the probability of having exactly 3 boys? So we have to first find the possible arrangements, and possible arrangements meaning what's the possibility of the order. So if we have 5 spots here, we can have boy, 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 girl, girl, or boy, girl, boy, boy, girl, any of these arrangements. So if you can do all of them and count, but we can also do out of 5 boys, choose 3. If you do this, this will equal 10. So this tells us that there will be 10 different possibilities. So this is the same thing. Out of 5 spots, choosing how many ways can I choose 3 of them and reserve that for boys. So we'll keep that number around, and the next thing that we have to do is exactly 3 boys. So we have to find that exact probability. So probability of having 3 boys is 0.51 multiplied 3 times. And the rest of the 2 girls must be girls, so the probability of having a girl is 0.49, and you're going to have 2 of them, so we're going to have multiply itself 2 times. And we have the possibility of 10 different arrangements, so whatever that this one equates to, this would be the answer for A, having exactly 3 boys. So then let's do part B. What's the probability of at least having 1 boy? And so this is the same thing as we can have 1 boy, 2 boys, 3 boys, 4 boys, and all boys. So the only possibility that it excludes is when we're having 0 boys. Having 0 boys is the same thing as all girls. So it's the total probability minus 0.49 to the power of 5. So that's the answer for having the probability of having at least 1 boy. C is pretty much the same concept as would be 1 minus the probability of having all boys. So that would be 0.51 to the power of 5, whatever that number equates to. That's the solution for C. Alright, so part D, the last one, all children of the same sex. Alright, so we could have all boys, which in that case that would be 0.51 to the power of 5, or we can have 0.49 to the power of 5. And in mathematics, if it's or, then we include all of those cases. So this equates to plus, so it's this 0.51 to the power of 5 plus 0.49 to the power of 5. That would be the solution for part D. Alright, so I think that completes the section. Now let's go ahead and do the following problems in the other section. I think this would be a good time to pause the video and do the reading of the textbook if you haven't already. So let's take a look at number 6. So all of these problems are part of the next section which deals with the Bayes theorem. For all of these problems in this section, I like to use the tree diagram to organize all the details that's given. Otherwise, it's very confusing, and if you interpret one given number wrong, then I think it falls onto the domino effect of getting all the numbers wrong. Okay, so in this case, we have this type of drug, steroids, given to soccer players. So we're first basing off of those two cases. Those soccer players getting the steroids or not receiving the steroids. So these are the two cases. And suppose that 5% of the soccer players do take the steroids, so that's this probability here. So this will equate to 0.05. This is the same thing as probability of S. That naturally makes this probability 0.95 because we do have understanding that both of these have to add up to 1. So this is the same. This represents the P of the complement of S, or probability of not S. Those players not taking the steroids. Okay, so within this, we have subcategories where the test result becomes positive or not positive. And same thing, for these cases, we have the test result being positive or it could be not positive. And this result is going to be 98% of the players taking the steroids test positive. So the 98%, that would go here. So I would put 0.98. So what this really means, this is the probability of getting positive given S. So this information naturally makes the other part as 0.02. Again, the entire probability needs to add up to 0. Sorry, it's add up to 1. So this is the same thing as probability of not positive given S. All right, so those informations we were able to categorize. What's also remaining is the and 12% of the players not taking steroids test positive. So that's this part. So this would be 12%, which equates to probability of P positive given not S. And that'll naturally also make this part as 78. This is P of not P given not S. Once you have all of our information just organized like this, now we can go ahead and solve for the problem, whatever they're asking. So they're asking that soccer player who tests positive takes the steroids. So they're asking for this value, probability of S given P. Okay. So our textbook gives us, or I guess the base theorem all about it is P of S given P. This is identical to P of P given S times P of S over P of S times P S plus P, probability of positive given not S, probability of not S. All right, so now it's all about plugging in the values. So probability of P given S, that's this value 0.98, so that's 0.98 times probability of S. We're looking at this value, so that's going to be 0.05. We kind of have to write the same thing again. And probability of P given not S, so that's this value here. So that's 0.12 times probability of not S. That's right here, which is 0.95. So whatever our calculation comes down to, that's the answer to number 6. So in a basic sense, that's what the Bayes theorem is all about, and we will, I guess in our next video, we'll do the rest of the 3 assigned problems. That pretty much repeats what we did, and if you practice drawing the tree diagram, I think you should be fine with any type of problems that utilizes the Bayes theorem.